All right, let's dive into a really fascinating data structure, the circular linked list. Now, if you've worked with standard linked lists, you know they have a very clear beginning and a very definite end. But what happens when your process can't have an end? What if it needs to loop forever? That's what we're going to get into today.
So just to refresh, picture your classic linked list, right? Each node points to the next, and that very last one points to null. It's basically a dead end, a hard stop. But then, look at the circular list. The last node doesn't just stop, it loops right back around to the very beginning, creating this perfect continuous circle.
And that really is the million-dollar question, isn't it? That null pointer is actually a limitation. It's perfect for a finite list of things, sure. But what about processes that need to run in a cycle, over and over and over again? You know, like a music playlist you've set on repeat, or how your computer's CPU juggles different tasks. They don't just stop, they have to circle back.
And this brings us to a really elegant solution. Instead of trying to wrangle a linear list into doing circles, why not just use a structure that was born to be a loop from the get-go? So what exactly is a circular linked list? Well, it's pretty much what it sounds like. It's a linked list where that final node, instead of pointing to null, points right back to the very first node, the head. That's it. That one little change completely transforms it from a line into a circle.
So this is the key. If you remember one thing, remember this. There are no null pointers here. The end is the beginning. And this is what gives it its superpower, the ability to just keep on going.
Okay, so we get the concept. It's a loop. But how do we actually, build one? Let's get our hands dirty and look at the logic and the code behind putting this thing together.
First off, some good news. The actual building block, the node itself, it's identical to the one you already know and love from a standard singly linked list. You've got your data and you've got a pointer to the next node. The magic isn't in the node. It's all in how we wire them up.
All right, first operation, let's insert a node at the beginning of the circle. Now, this is a little trickier than it sounds because it's a circle. Adding a new first node means we also have to find the last node and tell it where the new beginning is. Let's see how the code handles that.
So here's the game plan. Step 1, create the new node. Easy enough. Then, and this is the crucial part, we have to walk the entire list to find the current last node. Why? Because we need to update its next pointer. Once we've got it, we point our new node to the old head. And then, to complete the circle, we make that last node point to our new head. This also shows a little trade-off. Finding that last node takes time. It's an O of n operation.
Now, inserting at the end, well, it follows a pretty similar logic. The big challenge is exactly the same. You've got to find that last node and then carefully rewire the pointers to make sure the circle stays unbroken. The code looks a little different, but the core idea is identical.
It's like a little 4-step dance. You create the node, you travel all the way around the circle until you find the one right before the head, then you link that node to your new one, and for the grand finale, you link your new node back to the head, making it the new official end of the loop. So we've built our circle. Great. Now, how do we walk around it? With a linear list, we just keep going until we hit null. If we do that here, we're going to be walking forever. So we need a smarter strategy.
This code right here is how we can visit every single element without getting stuck in that infinite loop. And if you look closely, you might notice the loop structure is a little unusual. There's a very good reason for that.
And here's the secret sauce, a do-while loop. So why on earth are we using this? Well, think about it. We need the code inside the loop to run at least once before we check our stop condition. If we used a regular while loop and our starting pointer temp was already at the head, the condition temp not equal to head would be false right away, and absolutely nothing would get printed. The do while makes sure we process that first node before we even think about stopping.
Deleting a node, especially the head, is another delicate operation. We have to be super careful to make sure the last node in the circle knows where the new head is before we get rid of the old one.
And this breaks it down perfectly. Again, first thing we do is find that last node. Then we tell it, hey, you're not pointing to the old head anymore, you're pointing to the guy after him, the second node. Then we make it official. That second node is the new head. And only then, once the circle is secure and reconnected, do we finally delete the original head.
Okay, we've gone through the theory, we've looked at the code, but where does this stuff actually show up in the real world?
Let's take a look at how this abstract idea powers some of the tech we use every single day.
You see a theme here, right? It's all about cycling. CPU scheduling is a perfect example. A round-robin algorithm gives each process a little slice of time. When its time is up, it goes to the back of the line, and the system moves to the next one, eventually circling all the way back to the start. It's the exact same logic for your music playlist on repeat or managing whose turn it is in a multiplayer game. They're all just natural, endless loops.
So, to wrap this all up, let's just hit the highlights one more time. Circular linked lists form a continuous loop. The last node points back to the head. There are no dead ends, no null pointers. And because of that, moving through the list means you need a special stop condition, like checking if you've made it back to where you started. This data structure is just so incredibly powerful for modeling any process that is cyclical by its very nature. So I'll leave you with this question to think about. Now that you understand how to build and manage this endless loop, what other real-world cycles out there could be modeled perfectly with it?